An electric car accelerates from 0 to 60 miles per hour in under 2 seconds, faster than most hypercars costing several $1,000,000, and it does so without sacrificing range, without overheating, and without requiring costly maintenance. How is this possible? And why have competitors still been unable to replicate what is already being mass-produced in gigafactories? Over the past few years, Tesla has covered ground that the automotive industry typically measures in decades. First, the company proved that an electric car could be practical. Then it equipped that car with driver assistance systems that gradually evolved into fully fledged autonomous driving technology. Now comes the next step. And it isn't simply changing the specifications of a car, it's changing the very logic of competition within the industry. At the center of this shift is a new generation of electric motor design, built around a carbon-wrapped rotor. At first glance, it appears to be a simple change of material. In reality, it's the solution to an engineering problem that has been holding back the entire industry. Here's the essence of it. Every electric motor has a physical limit to its rotational speed. The faster the rotor spins, the more power is delivered to the wheels. But at high speeds, metal components begin to expand under the strain of extreme loads and heat. This leads to wear, reduced efficiency, and in the worst cases, mechanical failure. This is precisely why most high-performance electric motors operate within a range of roughly up to 16,000 revolutions per minute. That threshold has long been the ceiling for the entire industry. Tesla took a different approach. Rather than working within that limitation, the company reinforced the rotor with high-strength carbon fiber, a material known for its combination of extreme lightness and strength that surpasses steel. It withstands high temperatures, resists deformation under pressure, and maintains structural integrity under sustained loads. The result is a motor capable of operating at speeds approaching 20,000 revolutions per minute without overheating or mechanical failure. These aren't merely figures on paper. The gap between 16,000 and 20,000 revolutions per minute is the gap between what was the industry standard and what Tesla has achieved in mass production. And this is precisely where the chain reaction begins. The faster the motor spins, the sharper the acceleration, and the greater the power output. Hence the 0 to 60 miles per hour in under 2 seconds, a figure that until recently was the exclusive territory of hypercars with large displacement internal combustion engines. Bugatti, Lamborghini, Ferrari, brands associated for decades with extreme performance, now find themselves in the same conversation as an electric car that operates in near silence and requires no fuel. But here is what is fundamentally important. Speed is only part of the equation. Traditionally, more power meant rapid energy consumption. The harder you accelerate, the faster the battery drains. This was the fundamental trade-off faced by every electric vehicle manufacturer. The carbon-wrapped rotor changes that balance. Thanks to its reduced mass and greater structural efficiency, the rotor lowers energy losses during operation. Fewer losses mean higher efficiency, which means greater range on a single charge. Drivers gain both extreme acceleration and practical range simultaneously. The compromise that was previously considered inevitable has effectively been eliminated. Add to this the matter of durability. Conventional motors wear down under the strain of thermal and mechanical loads. The redesigned rotor construction significantly improves resistance to these factors. The motor retains its performance for longer, requires servicing less frequently, and the overall lifespan of the vehicle increases. For the owner, this translates to lower long-term running costs. There is another aspect that often goes unnoticed. The new design reduces dependence on a number of rare and costly materials traditionally used in electric motor manufacturing. This has a direct impact on production costs. Fewer rare components means simpler manufacturing, which means lower costs per unit. And this is precisely where the strategic dimension of this technology becomes apparent. Tesla built its manufacturing from the ground up around electric vehicles. It didn't adapt old factories, but created new ones from scratch, purpose-built for specific objectives. Gigafactories across different parts of the world operate with a high degree of automation and are designed for scale. The new motor fits seamlessly into this already established system. This means that the reduction in manufacturing costs doesn't remain a theoretical advantage, it is realized in actual production volumes. For competitors, this creates a twofold problem. Traditional manufacturers, such as Ford, General Motors, Toyota, and Volkswagen, are transitioning to electric platforms from factories originally designed for internal combustion engines. Such a transition is more expensive, slower, and structurally less efficient. Their electric vehicles are often heavier, more costly to produce, and less optimized in terms of electrical architecture. Newer market entrants, such as Lucid Motors and Rivian, demonstrate impressive engineering solutions, but run up against the problem of scale. Producing several thousand vehicles is fundamentally different from producing hundreds of thousands. Manufacturing bottlenecks, supply chain constraints, delivery delays, all of these factors hinder growth and drive up costs. Without large-scale production, even competitive specifications don't allow a company to go head-to-head with one that can deliver quickly, consistently, and at global volumes. BYD warrants a separate discussion. In terms of overall electric vehicle sales, the Chinese company has moved ahead. However, its strategy is built on affordability and mass market reach. When it comes to advanced innovation in motor design, battery optimization, or software integration, Tesla retains a notable advantage. BYD reaches more buyers, but the technological gap remains. Now, to what makes Tesla's position genuinely difficult to overcome? It isn't a matter of a single breakthrough. It's the fact that several critically important technologies are working together as a unified system. First, the battery. A next-generation cell of a larger format, more deeply integrated into the vehicle's structure, delivers greater energy density, higher power output, and an extended service life. This directly addresses two historically weak points of electric vehicles: limited range and lengthy charging times. Second, artificial intelligence. Every Tesla collects data on real-world driving conditions, cornering, braking, unusual road situations. This data is processed and fed back into the system in the form of improvements. The more vehicles on the road, the more data is generated. The more data, the faster the system develops. It is a closed loop that reinforces itself with every kilometer driven. Third, software updates. Unlike conventional cars, which remain fixed after purchase, Tesla vehicles continue to evolve. New features, performance improvements, expanded capabilities, all of it arrives over the air without a visit to a service center. The car doesn't become obsolete, it gets better. When the motor, battery, artificial intelligence, and manufacturing infrastructure all function as a single whole, this is no longer simply a collection of technologies. It is a systemic advantage, and systemic advantages are the hardest to replicate because copying one component isn't enough. The entire architecture must be reproduced. Most competitors are solving problems one at a time. Some are working on range, others on charging speed, others still on software. Tesla is doing all of it simultaneously. This is precisely why the gap is widening faster than analysts anticipated. Yet the history of industry contains examples of seemingly insurmountable advantages that were, in the end, overcome. The real question now is not whether Tesla is leading. That much is clear. The question is who, and by what means, will be able to close that gap. Will the traditional giants be able to reinvent themselves quickly enough? Will any of the newer players convert engineering ambition into manufacturing scale? Will a breakthrough emerge that nobody has foreseen? There are no answers yet. But one thing is clear. The carbon-wrapped rotor is not the final chapter in Tesla's development. It is the foundation of the next phase, and that phase has already begun. If you're interested in following this story as it unfolds, subscribe to the channel and give it a like. It helps us produce more content like this. See you in the next one.